Okay, howdy folks, and welcome to Project NESnet. This is day number, I wrote 5, but I don't know if this is actually 6. Day 6. So we're connecting the NES to the internet with a Wi-Fi chip, ESP8266. I got some debug wires here connected. So just kind of review of where we're currently at here. We're using the INLretro as emulator for the console side, so that we can test out some of the hardware stuff without having to write test ROMs and do some debug that way. So right now I have socketsv host. My host PC here, my streaming PC, is a server running as a server with socketsv, and it basically is just listening to incoming TCP and UDP and WebSocket packets on port number I forget, but so it basically, we can use it as a print log instead of using like a serial connector. So the ESP, here's our ESP code. This just connects. I have hard-coded in here my host PC's IP address, and then here it's port 1234 that Python or the socket server listens to. So when the ESP boots up, the UDP, we can do other types too, but we're just doing UDP for now. So it will start sending data to my local PC. It first just has some initialization things set up, and then last time we enabled interrupts. So we have an interrupt service routine when the meso pin goes low on the ESP. We call send GPO UDP, which it does a SPI register bitbang on the CPLD to read out the data. So it toggles clock high and low, and then it reads the meso pin, collects the byte, and then it sends a UDP packet of what it found. So here we can see we ran a test, and we'll go ahead and do it again here quick, but this is the data that it read. So we have a Lua script running with INLretro, and here's what it's doing. So it's writing. This is what the console will be doing maybe today. I don't know if we're gonna get that far today. I can only go to about 1:30 or 2 or so. Anyway, it writes to the 5000 register, which is on the CPLD, which we're developing with even more code. There's a lot going on here. I think it's this one. Yeah. So here's our verilog that we synthesize with ISP lever and then flash onto our CPLD. So this verilog has the SPI register. This 6502 writes to it in parallel, and the ESP reads out in serial. So it's writing 1 to the 5000 register, then it writes 5, 8, A5, C3, FF. So previously we had it where it's polling, but now we have an interrupt, so we can just write that data one after another, and then just spit out the data over again. So what I'm hoping to work on today is we have everything working up to the point to where the 6502, just INLretro for now, but hopefully we won't have problems when we switch over to the NES. But the 6502 can write to the 5000 register. The ESP gets an interrupt, retrieves that data from the register, and then sends the UDP packet to the server that it's not really a connection, but it's programmed to send it to. Now, we will need to set up a communication protocol to where the ESP then, so it reads that byte and that'll be a command. Here's kind of a rough plan of what I've got. So I want to keep this as condensed as possible, and I'm using the rainbow. I don't know if I have is this it? No, that is not it. I'll find that link. I'm not going to worry about it right now. Anyway, Rainbow is developed by Broke Studio. I always have to think about that. The general format of the commands is the first byte is the length of whatever's to come. And then there's a 1 byte for a command, and then there's a byte for how much ever data you have. So if we were just going to send one command with 1 byte with a 1 byte argument or something, a piece of data, right? Length would be 2, because you'd send. So you'd first write 2, then you'd write the command, then you'd write the data. So 3 bytes total, but the first byte's equal to 2 because there's 2 bytes that follow. We can. I've got a plan to because the 6502 has to pull the 5001 register before it can send more data. I want to try to condense these commands as much as we can. And so this is kind of the format that I have in mind here, where we can get things done with just a 1 byte command. Most common type things. So the lower nibble will effectively be our length. Now that only supports up to a 15 byte message, or no? Yeah. Message or data, whatever you want to. 15 bytes worth of data that follows. And then the general format for bit 7, the most significant bit, will be whether or not the 6502 is sending data, it's writing to the ESP, or if it's requesting data to read. So basically, what's going to happen with the bytes that follow? Is where's the data coming from? Which direction are we going? And then bits 4 through 6 will be this, like, it's almost like instruction format ISA, instruction set architecture mentality here with these other 3 bits. This is kind of like the addressing mode of some sort to define the other bits that follow. So my thought is, so the most common length type, you read or write 1 byte. Okay, so I think that's where this becomes the byte number. So I have immediate addressing. I can't make sense of this. Oh, okay, here. So the first byte anyway, somehow we're going to denote that with this command. We would have to send the variable number. Now, conceivably, we could have that here. Here's immediate right here. Here we go. So we're either reading or writing this variable in the ESP. Bit 6 is set to 1 for this immediate instruction type, and then bits 0 through 5, these other bits end up becoming the which variable number are we reading or writing to. So if we wanted to say read variable 0, we would clear bit 7, set bit 1 because we're using this address mode, and then all the other bits would be 0. And then we would wait because the 6502 is wanting to read that data from the ESP. So we'll use the 5001 register to denote when that data is ready to be read from the 5000 register. So in this case, where you're just reading in a single byte, you write this 1 byte command that says which variable number we want to read. The 6502 will pull 5001, and the ESP during that time will be fetching that variable and writing it to the SPI register and set the 5000. We haven't created that 5001 bit for read yet. We'll have to do that. And then for write, it would be the same type of thing, except we would set bit 7. We would set bit 6 because we have this addressing mode, and then the other bits would be whichever variable number we're reading or writing, or we're writing. And then so we'd write that to 5000, but then we would need to send the value that we want to write. So we would pull 5001 until the ESP fetched this instruction, this command, and told us that it's ready for the next write. And then the 6502 can write the next the variable, and then the 6502 can effectively be done. The ESP will then go process that and update that variable. So so let's just try to implement that. I have other ideas for, when we want to do more complicated stuff. An addressing mode. So if bit 6 is clear, then it's either medium or long addressing mode. Bit 5 differentiates between if it's medium or long. medium, we can denote the length with the nibble, the lower nibble. So that allows us to read or write a 15 to 16-bit message. And then if we want to do more than that, we can set bit 5. Or wait. I don't think I... Oh, here's long. Right. So medium, you denote the length in the lower nibble. Long, we could have some compatibility with rainbow mode. We could do different stuff in the lower nibble, don't really know. But the next byte would be the length. And then we could do special stuff with this bit number 4. So if we have a very specific command set of, you know, checking Wi-Fi networks or something, I don't know, to where we just want to tell the ESP to go do some defined command, we'll set bit 4, and then we can put a command in this lower nibble. Anyway, that's just kind of my general idea. I think that will cover most cases. I just want to start with this first basic one, though. I suppose we should start by implementing the read bit. 5000 bit 6. So that hopefully will be faster than last time. We had lots of debugging for figuring out. So this is kind of what we did last time. We had in red here, we had an 8-bit shift register. I made it a 9-bit shift register by adding the W bit to the end. I think what we're going to do is wedge the R bit in there, so we'll make it a 10-bit shift register. So we'll put R here and W here or something like that. Should be relatively easy to change it around. But this W bit is what's being used as the interrupt for the MISO pin. So that one needs to be last, because it'll be the furthest to it needs to be the first one out. So let's just try to implement that guy quick. So we'll try to follow in the footsteps of our W status bit. This will be R. We need to be able to read it out of the 65 out of 5001. So this makes the bit readable on the data bus. So when reading from 5001, it will output this, and this will be the status R bit, and we're going to put it on bit 6. Now what, I don't know if we'll have to actually, we had to do this ANDing. Oh, I think maybe we will have to do a similar type thing, because we don't want this read bit to change as the data shifts through it, and so we'll block this value. Hey, thanks for the oh, so you're gonna have to tell me how to, is it Hitch? Hitch is hosting me. Thanks for the host, Hitch. I'm gonna guess that the 7 is pronounced as a T. Okay, all right. Thanks for the host. So we're trying to implement a extra bit. We have a register at 5,000, so we want the 6502 to be able to tell when the ESP has so we want to be able to have variables inside the ESP effectively. The 6502 will write to this register, and then the 5000 register, and then the 5001 register, it'll pull that, waiting for this read bit to be clear, and that will indicate that to the 6502 that the ESP updated the variable, and now it can read the requested data in 5000. The data is actually going to shift through this R bit, so that could give us a false indication of the data being ready, because there's going to be zeros in this. So we'll block that with the control signal. So when this ESP is shifting through this register, it's I forget the value of this, high or low. It'll be low. Anyway, so we'll do just like we did before, where the value that the 6502 reads is ANDed with that signal, so the ESP can override the value to 0. Okay, then we have to update the shift register here. So I don't know. So this is when we're doing the W bit, the write bit. Anytime that a parallel write occurred, we had to clear it to cause the interrupt. What do we want to do with the? So we're gonna say that 0 means that the bit has been retrieved. I don't think it matters what we actually set this to. Well, let's set it to 1. So we just need to decide. So we'll say that building your DOS machine, soldering with the Wi-Fi 65 much easier than this. Just saying, yeah. The we've got a little CPLD here, and it's the mapper chip of the cartridge. These guys are pretty common. With the original, where's my? Here we go. All right, I'll give you a quick glimpse here. So we'll just click this one. What do we get here? Okay, so this is some Japanese pro basketball game. MMC. This is an MMC1 mapper chip. Kind because the 6502 only has 64 kbytes of addressable space, whereas like the Commodore 64, right, has RAM and all of that. If you want, you can have bigger games right on the floppy drive or whatever, right, and load that into RAM and execute it from RAM, and you know, your entire address space is that RAM buffer, right? Well, the NES doesn't. It only has 2K of RAM, and so this cartridge, the instruction ROM, right, the game ROM itself, where the code and data is, this gets generally mapped to 8,000 and above, so the upper half of the 6502 address space. This chip is the tile data for the graphics on a separate bus, but the 6502 to get the NES to get access to more than 32 kbytes of code and data will end up using bank switching on this chip. So this mapper chip will bank switch this chip, so it controls the upper address lines. And so my brother manufactures, I design replicas for these mapper chips and boards. I've got, this is a bigger guy here. This bigger chip we use for some of the more complicated mappers. But anyway, we make these boards, and so this is kind of my routine gig here. And then we're just tacking the ESP onto it. So we're basically putting registers inside this mapper chip, and then the ESP can talk. So both 6502 and the ESP can talk to each other through the mapper chip is how the 6502 doesn't have direct access. Just because we don't have, it would be nice if we could. Well, and I guess to some degree, maybe we could, but it would have to be via serial. It'd be pretty. It put a heavy processing load on the 6502 to send data. We'd have to have big bit banging routines, and so this just makes things faster. To put this shift register. So we're gonna say that a 1 indicates that. I mean, the ESP is gonna clear this, but just mentally. So happy guys like you and your bro are doing this. Thanks. Makes your life much easier to keep this gear going. Upgrading, or hell, just playing the hardware. Yeah, we have a lot of fun with it. All right, so we will did data not ready, we'll say. So anytime that the 6502 writes to the 5000 register, we'll set this bit because, of course, the data is not ready. We just stomped it, and then we have to and put this bit inside the shifting. What did we say? The R bit is going to be here. So 7 through 0 of the 5000 register, and then the R bit, the W bit. So this will be the first bit out. Now when we're shifting in, we have to put the R bit over here. It's kind of hard to see that from the code, but this will become bit 7, right? So the left is the most significant bit. This is the before, this is the after. So the least significant bit will end up here, right? So the R gets shifted into the W. bit 0 of this byte register gets shifted into the R, and then bit 1, so forth. The MOSI pin gets shifted into bit 7 of the SPI register. Okay, do we need anything else? I think that might be it. Life is based around pop watch. Best to follow your orders. We'll see in a bit. All right. So let's synthesize this. I'm surprised that this didn't detect that our changes took effect, right? Or we have the right project open? Yeah. Oh. Nope. Oh, there's some of it. Status R. Oh, I just didn't. I need to fix this. So this is going to be status 6. I should just use that one. So update our comments. This is the write status register, or whatever, just status register. Okay. What was our, let's watch our use. Oh, it's gonna, whatever. I forget how much logic we were using previously. I kind of like seeing the logic consumption increase as we add features, just as like verification that yes, our new logic is consuming logic. So it's probably in there. 24. I feel like we were at 22 before. Anyway, let's just assume it works. Did he actually make the JTAG file? We gotta plug into this guy to program it. Detect device, not so much. My wire's bad. What's going on? Hey Dizzy, doing well. How are you? Be doing a little bit better if my JTAG programmer was detecting my device. I don't know what's going on here. Maybe I should just unplug this. I thought this thing felt a little warm, but maybe not. Let's try it again here. What in the hell? Check my wires. If this looks good. Try again. Okay, error connecting to target board. Although it was saying JTAG, I don't know what that was all about. Failed to connect to JTAG device. Let's try this then. Let me connect a different cartridge. This has got a different CPLD on it. Doing some work. Okay, that connected. I hope we didn't break our cartridge somehow. Gosh golly. The CPLD is working, isn't it? Okay. Okay. Everything's working. I wonder if I can... if I can talk to JTAG from my INLretro. For whatever reason, it will flash and verify CPLD, this type of CPLD, but it doesn't actually, the new configuration doesn't take effect. It seemed like it did on my Super Nintendo board, but it's definitely not working on this board. But this will at least tell us if let's just try to erase it. Although if I erase it, if I can't reprogram it during the stream, I might not want to erase it. Don't want to use that. I guess it doesn't matter what file we send it, we're not actually going to flash it. Well, it read the ID code. I wonder if my FlashCat, well, my FlashCat programmer is working though. It connects to the other CPLD. Let's try same CPLD, different board. Stack of cartridges over here. How much on this one is? Can't see. Okay, so this is a 64 macrocell device. It's twice as big, but it's the same type of. I don't know. This. JTAGs. Let's just try. weird problems last time. Maybe some of my cables are bad. With this Wi-Fi cart, finally have Smash Bros. Online. There you go. Speaking of, one of the guys that's working on this, I always choke remembering their name. Super Tilt Brothers. Super Tilt Bros by Sylvan. He's actually oh, you saw that? Cool. Yeah. So he actually has this. He has a build that works online. Oh, he's got. You're gonna sit here and play in the browser. Yeah, he has an online version of this. There's no what's the word? Cartridge, or maybe he. I'm not 100% sure. I don't think he has it working on a cartridge yet. Just a emulator. There's that. But yeah, so that'll. Yeah, so we'll have Super Tilt Bros. Yeah, check that out. That one will definitely be online. Okay. So I don't know what's going on here. I'm gonna try a different USB port. I don't think that's gonna have anything to do with. I don't think that my cartridge is broken. Because this other CPLD detects. It's the same. Let's just load script. Yeah, we should be able to. Maybe this. Am I running the wrong version of FlashCat? Yeah, well, yeah. I mean, to some degree, the sky's the limit. Whatever we'll have, whatever people decide to implement. I like the idea of like the server code. Well, so I like the idea of there being P2P options where somebody could release a game with, as long as you have 2 cartridges and a Wi-Fi router that this guy can connect to, then 2 people can play together. Now that might be just your friend, and you have to like text them your IP address or whatever so that you can connect. But it would be serverless in that case. Kind of future-proofing it to some degree. I mean, future-proofing it as long as people have Wi-Fi routers that support this guy, which doesn't seem too crazy. But you're somewhat limited in what games you can do with that type of style, and finding random people online to play with could be a challenge. But you could have like a Discord server or whatever is fashionable at that time, where people just go on and say, "Hey, I'm playing this," and then put their IP address and you can connect. But it would obviously be cooler or better. You could do more things, more powerful, to have a server running online that You could have like rooms to connect to, upload high scores, you know, do whatever you wanted. Games to download and try out. If that code was open source and you know, multiple people could implement that server, I could put it on my website. There could be on, you know, NestDev, or whoever wants to host a server can. And then if a server goes down, it's not like, oh, all these games worthless. Like the server code's open source, anybody can implement it and keep a server running. Yeah, I mean, you could do level generation. I mean, there's really, like, once you get into that end of it, like, you can write unlimited, you know, code from the server side to do things, as long as the hardware supports, like, has RAM on board or a flash can be updated. Like, you could even, I feel a little bit differently about like a digital marketplace where you could buy games. I don't know, like, just dealing with money gets messy. But to some degree, developers could do whatever they wanted if they want to do the server side stuff. So that's up to them. But it would be cool at least to have like just free games people upload and is compatible with the hardware. So let's see. I'm gonna try. A different version of my FlashCat software here. Okay, so this guy actually says Lattice Mach XO 256. Yes, to some degree. But or a subset of the mappers that it can also support. Yeah, DLCs, purchase patches for, you could have subscriptions to your game where you get loot boxes and stuff. Yeah, this is not. Does not. Yep, that's perfect. Huge. I'm gonna just make sure that the programmer is working with this other CPLD here quick. I just stare at my giant. I don't know how to make this smaller. I can't do it. I thought that this would no longer be massive when I restarted my computer, and it's still massive. The little corner to change the size does not. Searching for CFI flash. You hear Bandit down here barking in his sleep. Something is going on with my. Why is it doing this? Oh, it's going. Error. I wonder if it's. I'm gonna try a different set of wires. It might just be that my little wiring setup with this guy is no longer good, but let's if this doesn't work, then we'll just focus on the ESP code today. Pretend this bit is gonna, or acknowledge that it's gonna be there in the future. I have to figure out why my JTAG code doesn't work on these old CPLDs. They're smaller CPLDs. Okay. I just have this crusty old kazoo wired up to give me access to the expansion port. This FlashCat software is... See there, it's supposed to do that. It's supposed to just do, as soon as you detect SVF player, let's try. That's a good sign. Maybe my wires are just getting broken. Flash this guy with... It still does this searching for CFI flash nonsense. It's flashing. Error. Try this one. I'm going to say one more time, a lot more times. I feel like it's related to this nonsense. Yeah. Not... This is a different build. Detected, load script, SVF. It's not saying it's CFI nonsense. You guys have to let me know if I'm having issues with the stream. For some reason, last Wednesday's stream, hey, that went. I was dropping, it said I was dropping frames. Couldn't figure out why. I went back and kind of watched a little bit of the stream. Oh, it's working. Okay. Let's put the actual, I tried that other one. Detect device. Hey, I need to I think maybe, oh, you know what? I think I was clicking the wrong. I have these Flashcat things on here, and these are old ones that I should not be using. I think that was my problem. But if you're seeing issues with the, all right, take care. If you guys are seeing issues with the stream, like I'm dropping frames, stuttering, and stuff like that, let me know. I'm only dropping, well, I've dropped 1,000 frames, but it says that's 0.8%. I don't feel like that's a very good calculation of percentage. If I'm 30 frames per second, I've been going for an hour. 1,000 frames is, anyway. Let me know if there's issues. This does not resize. This is ridiculous. All right, what's our build? Spent the last 20 minutes trying to flash a CPLD because I clicked the wrong damn thing. Good game. Oh, good job. Gotcha. Thanks. Okay. Okay. I think we flashed it. Now, we have to update our ESP code. Where did I throw that thing? Oh, there it is. Just gonna let's use let's not worry about the debug. Let's hopeful thoughts here and assume that we can get by without debug wires. Let's just go for it. All right, so we have a bigger register now. We need to shift 10 bits now. But because they're lower bits, they'll just disappear, and we'll still be setting the MOSI bit high, so that it'll set the R bit and it'll set the W bit like we want. Okay, now let's change our mask of the 5,000 of the bits that we care about. So we care about the 2 upper bits, and so we should be able to read those. It should always be set. Okay, I think we're ready to go. We need to recompile and flash our ESP. Installing platform IDE. I just want to do work. I don't want you Like this has been spinning all. You're not earning any bonus points today, Visual Studio. It's exactly what I don't like about IDEs. Oh, let's run an update. I can't like compile the project in Vim and Flash. This is my best means of compiling and flashing. Now, you can use Platformio in the command line, and I think that's really where I want to go to. It seems to be okay now. It gave me that requesting update. There's a lot of pots. Well, you didn't miss much because we spent 20 minutes figuring out that I opened up the wrong JTAG programmer software and we couldn't flash our CPLD. But we figured it out while you were washing your pots. Okay. So we flashed our ESP with new code. Let's plug this puppy in and make sure that what was previously working is still working. After we added in our read status bit. Okay, so it looks like it booted up and sent this. We'll run our script. Oh, I swapped my cables around. Okay. How about meow? Not JTAG, this one. Okay. 158A. Now it looks like we might have lost the other. So what happened here? We wrote A, then we read back 5000. We had FF as if the ESP fetched it. We wrote A5. Yeah, why didn't we get all of our... Let's try it again. It looks like the ESP was fetching it from the cartridge side, from the INLretro side. Here we go. 158A, A5. The last byte, not so much. Anyway, part of the thing is my current code is not checking to make sure that that the bit is clear, it's allowed to make another write. And these earlier ones, I'm checking the 5001 register, which adds a little bit of delay instead of just write. The only I have delay here just inherent to USB requests not being able to be super fast. Okay. Hey D-Rocks. How you doing? So let's we're working on our Wi-Fi cartridge. So we want the we're starting to get to the point where we want the ESP to now the 6502 and the ESP can talk to each other through our shift register here. So this the NES writes to the 5000 register, which is an 8-bit. Well, it's 8 bits of this 10-bit shift register, but anyway. The 6502 writes, it can read from it as well, so 5000, it can read and write to this register. The ESP only has 4 pins. It has 1 pin for parallel load, so the ESP controls whether or not this register is in serial or parallel mode. So the ESP is kind of the master here, deciding what happens. So when the ESP allows it, the 6502 is permitted to write to this register. When we got our verilog code here. So when there's a parallel write to this register, these other 2 bits, we made it a 10-bit shift register, but these automatically get written to 0 and 1. And then this W bit getting cleared will interrupt the ESP. The ESP reads all these 10 bits and it can load in whatever data it wants. Right now it just loads in all ones. So we want to load in something else. Now it can, whenever it's just reading, it's quicker just to, because the ESP writes while it reads. Sound pretty awesome? It is. It's not too crazy yet. So we have the INLretro acting as the 6502 as we'll eventually write a test script. We might get in that today, or not a test script, a test ROM, an NES test ROM, so we can plug it into the NES. But so we're just emulating the NES, and it's reading and writing to these registers, and makes it easier for developing and debugging our code that's running the ESP. So, brain got fried. I don't get anything of it. Yeah, thanks for stopping by. Well, and we're still pretty low level stuff right now. So, you know, maybe once we get out of the low level hardware weeds here, some of the stuff will be, when we get to making games that are actually doing stuff, it might be less. I'm hoping we can provide some abstractions that'll make things easier to understand. So, okay. You're fine. Level 1. Okay, so here's our send UDP. So this is our interrupt service routine. Whenever that bit goes low, that last bit that automatically gets set, ESP gets a interrupt and it goes and processes. So for right now, we're just sending UDP packets of whatever was read to my host machine that's running as a server. So let's make a new function similar to what we had before, and this will just be fetch spy byte, or byte, I guess. Is there a way for me to make this bigger? I don't know if you guys can see it very well. Bring this over here. I don't like the Vim editor in Visual Studios, but whatever. Good enough for now. It hasn't frustrated me to the point where I've given up on it. Okay. So in this routine, I'm not going to send any UDP. Sending the actual packets, like, that's kind of slow. We want this interrupt service routine to be as fast as we can. We'll still do the UDP packet as kind of like a debug at this stage, but well, let's not expect anything yet. Let's just get into it. See, that's why can't I'm selecting all these things. It only, I can't delete multiple lines with visual select. Like, that's just like a built-in default Vim feature. Why? As far as I know. All right. So spy int, let's change this guy. I'm going to name it the same thing so I don't break my other code, but this isn't really the interrupt pin like I thought it was going to be. This is just the control pin. Only, yeah, I don't, whatever this built-in Vim extension for Visual Studio code is, I'm not impressed. Yeah. Select all, delete it. Okay. I want a different define. So spy control, can I just define control do I want to have to spell it parallel each time? I'm gonna we had a problem last time because I left this pin in the wrong state. I copy paste errored and just, oh yeah, you'll remember high is low and parallel, whatever. So is the lowest level of the comms between the wireless cartridge basically we've got different levels of stuff going on, right? So you've got your ESP, or you got the 6502, right? Your code running on the NES. Then we have, and we haven't touched any of that. I'm not sure I understand your question, so let me explain this and maybe I'll answer your question, or you can ask again in a way that I'm understanding. So we haven't even actually written any assembly code for the 6502 yet, but we're emulating that with INLretro, which can make reads and writes to the mapper. So there's that level, right? The 6502 level. Then there's the mapper that the 6502 is talking to. The mapper, where you can implement this in like discrete logic, but we're implementing on a CPLD in which so I'll just keep explaining here. The CPLD is the mapper of the cartridge. You can have mappers just with discrete logic chips with flip-flops and stuff like that. We're using a CPLD, which is just programmable logic. We're writing that code in verilog. It's not really code. We're describing hardware in verilog. That gets synthesized into a bit stream that configures the logic inside that CPLD. So we flash that guy on. Now, the mapper, the logic here is like literally where the signal control is going on with all of the different lines. Gluing the ESP to the ESP pins to the data bus of the 6502. So we put a register in there that the 6502 can write to, and the ESP can read from it. We did that with a SPI register. Yeah, so right now it's a 10-bit register. 8 bits of it is what the 6502 has access to read and write from. 2 of these bits are kind of, so the 6502 can read these, but it reads them at a different address because the bus is full. So we have the CPLD presents these 2 bits at 5007 and 6. We can juggle them around if we want, but and the ESP has 4 pins. It has a parallel control pin, which is the one we're just writing code for. It has a clock pin, which we toggle to shift data through this register. And then it has MOSI, so master out, slave in. So the ESP is the master. So this is the ESP sending data to the shift register. And then there's a MISO pin, master in, serial out. So at the end of the shift register is the shift register is driving the ESP pin, and so this is where the ESP reads from. And so right now we are writing code that's running on the ESP to twiddle these bits, the GPIO that it has available. Yeah, miso soup, miso pins. So now the ESP itself, it's basically just a microcontroller that has hardware for Wi-Fi built into it. There's a little antenna on the board here, but so here's the microcontroller itself. The microcontroller only has SRAM. There's no instruction ROM in here. It loads it via basically they just want to make this chip as cheap as possible. RAM and logic silicon processes are different than flash. So putting flash and RAM and logic all on the same chip is expensive in the sense of silicon fabrication. So at least that's as far as I understand, that's my guess as to why they have the instruction ROM out here on a separate chip. Normally instruction code for a microcontroller is all in the same chip. Even small, need a coffee refill here, 10-cent, 20-cent microcontrollers have the flash. The instruction code is flash internal to the chip. They didn't go that route, and I'm sure it made the silicon smaller and cheaper processes. So yeah, just those 2 chips. You've got an oscillator and some capacitors and an LED and this little PCB antenna. It's just a trace on the board. But yeah, so this guy has hardware to be able to talk to the air. Now, there's a bunch of Arduino libraries written for this guy. And there's different frameworks available that are out there. But one of the most popular is the Arduino. I don't have yeah, this is it here. So there's a whole library available to this guy, and I haven't even really done, I'm using it, but it's just a black box to me. So all I do right now, probably have to get into it further at some point. But so I do a UDP begin, right? Which IP address do we want to send to? This is just the IP address of my local machine here. And then which port do we want to use? So to use this library, we begin. This is, I guess, initializing the library's functions or whatever. Then we can do begin packet, provide the IP address. What's this? I think local port's the, yeah, so the port number. Yeah, so here's a hard-coded version of it. Then we just write text, UDP write. We can do that multiple times, and then when we're done, we just call end packet and it sends it off. There's similar things for TCP. Establish a TCP connection with a certain IP address, and transmit messages. There's other libraries out there for WebSocket, which I'd like to support. Yeah, so this code base is that whole range from twiddling pins, the interface with the mapper with the CPLD, and twiddling the the library controls, has the code that twiddles the antenna to do things intelligently. So we want to fetch the SPI byte, and we'll probably return the byte that we fetch. But so the SPI control pin, the first thing we need to do is we have to take this pin low. This changes the shift register from parallel mode to serial mode, is how we designed it. So control parallel, right? Low, okay. And then when we're done, yeah, this can't even scroll. Oops, that's not the right thing. So SPI here at the very end, SPI control, we'll take it high. Okay. So that we're going to be set the SPI register in. Oh, I just got it all mixed up. Let's verify ourselves. So SPI int equals 1. We're actually going to change this to SPI control. So SPI control high for parallel. So parallel is high. Don't forget parallel high. Parallel. Low. See? I'm messing it up. High. Parallel high. Serial. Low. Okay. We want this to be serial mode, not parallel. See? The number of times that I've caught my bugs in writing a comment that disagrees with the code that I just wrote or I'm about to write. Do we need a comment here? No, but I'm in the habit of doing that. Very few times am I like, the only thing is like keeping comments updated, like is your comment actually true anymore? But no one wants to know that comment helps in any way. No, comments are good. See, I just proved it to you. Set spy reg to parallel. So 6502 can write again. All right. Now in the middle here, I'm not gonna do this. I want it. Oh, let's do this to do spy reg len. Let's define that so we don't have all these magic numbers. Define spy reg len 10. 8-bit data plus 2-bit status. So we're going to just going to so the first step is allowing the you to write the hardware config info to the NES. Does it relate to setting up memory banks, etc.? No. This stuff is the stuff that we're doing here is just this register that we created. That's at address 5000 range. Now the CPLD does also control banking and stuff like that, and we'll get to that eventually, but 32 kbytes is going to be, this is literally just a chunk of logic that has 2 ports on it, right? It has one port for the NES to be able to read and write from. It happens to be parallel. And it has another port, a serial port, that the ESP can read and write from via serial. So the reason that I chose parallel and serial, well, parallel on the NES side to make the slower processor, yeah, very low level right now. So the 6502 is the slower processor. Anything we can do to let the processor, the 6502, communicate faster, the better. Just because it's the most constrained, and we want to make things easy on the 6502 programmer, on the NES programmer, the developer, I should say. Now these little, I don't have to use, and I probably won't always use it. But these little ESP01, so this is the ESP8266 chip, happen to be using an ESP01 module, which is everything you see here in this picture. Only 4 of these 8 pins are GPIO going to this. I think there's only 16 GPIO on this chip, but only 4 of them are pinned out on this module. Now we may, I will probably end up using a module like this that has more GPIO pinned out. This setup is the setup for the base core communications between the NES and hardware. Yes, exactly. This is our glue logic between the two. So we only have 4 pins available. So that kind of, I'm limiting myself to that. I want to try to get it working with that. This processor is running at 160 megahertz, like 100 times, an order of magnitude, or 2 orders of magnitude faster than the 6502. But the actual data, because we're doing things serial, we connected up a logic analyzer last time. So here's the actual signals going on. I didn't save that other one, but this pin was our parallel load pin. So this pin changes. Here's the clock going high and low, and here's data coming out of the MISO pin. So this code that we're writing right now is twiddling these pins. So we'll do this, and then we'll take a look at the we'll connect up the logic analyzer at some point here. Probably when things stop working and we have to see what's going on to figure it out. Yeah, it does help. It helps me, and I'm sure it helps you guys understand. Now, am I writing code in 2 different? I have 2 different functions, and I started modifying. That's where I'm confusing myself. Okay. So we get the interrupt, we call our, well, I guess, I don't know, maybe we don't. We'll keep this in a function. I don't know if that's how we're going to stay, but so we go to serial mode, right? We take that pin, I can't remember which direction, serial. We have a data byte, and we are going to shift the data out. So taking the SPI clock high actually doesn't do anything, because we have the logic set up to be on the negative edge of SPI clock is when things happen. We actually have 2 different clocks being ORed together here, but right now we're just thinking about the serial. Either way, it's the negative edge of when things shift. But we had problems before where the drive strengths of this stuff was too low and the data was slow to come out. We have to take the clock high at some point anyway to be able to take it low later. So I decided just take it high right before we pull the MISO bit. So this is mostly just an indication of here's where the code takes it high. It's some period of time after that when the ESP is actually reading the status of this bit. So we have to do it. We may as well do it at some point that lets us debug things, better see what's going on. We can't see a read. We can only see a write from the logic analyzer. So we're going to sample the MISO pin. If the pin is high, we're going to add we're going to add hex 80, which is binary 1000, right? Then we're going to shift out the next bit. So in this for loop, the first thing we do is we shift the data over, so the 0th bit will be clear. Right? We set it to 0. The 0 bit will be clear. Now we'll set it. If that was high, we'll set it, and then we'll clock out the next bit. So then when we come back into this for loop, we'll be able to read the next bit. Now we lose the W and R bits because we're not storing them anywhere. We have to shift them out to be able to see the earlier bits. But the ESP doesn't really care about them in this setting. Hey Meatball, how we doing? Yeah, madman. I try. Yeah. Now when we have, so this gets us our byte. We have our byte of data. Now instead of sending a UDP packet, let's just comment this out for now. Let's just return so we don't actually need this clock high here. I just did this for a indication of when the interrupt service routine was getting called. Now I just want to make sure that this function isn't relying on this clock pin to be high. I think the first thing it does is takes it high. Yeah. We'll have indication of our, yeah. Well, so it's not. Well, Arduino itself is hardware agnostic, I guess, to some degree. It's just a library and a development environment of these ENO files, which are watered down C++ files. There just so happens to be an amazing library for this ESP chip we're using, written for Arduino. There's an Arduino library for this chip, and it's pretty easy to use, and so we're sticking with it. Allows programming without a programmer. Well, you can't. I assume you mean program a microcontroller without a microcontroller programmer. I mean, you can't program any microcontroller. I mean, I guess you can have a microcontroller that updates itself, but for the initial programming, and most Arduino stuff is the board that you're most often using includes a programmer, but all the programmer really is just a serial adapter to USB or whatever. Yeah, ESP, there's two different ESP chips that I'm aware of anyway. There's the 8266, which is just Wi-Fi, and then this one's a few years old. And then there's ESP32, which was released in 2016. So this is the earlier August 2014. So this chip's already 5 years old. Anyway, so fetch the SPI byte. I think this code here converted I tried to yank, but I bet you I didn't yank all those lines. Let's see. Yeah, one line. Okay, this might be the death of me using VScode, Vim. I mean, I could spend 5 minutes, 10 minutes trying to figure out how to multi-line yank. Or I can do things the way I want. And that is in the command prompt. Oh, but my Vim doesn't know what the hell an INO file is. I have to fix something. Let's see if there's a simple fix. Yeah, this person seems to agree. Oh, they tried a different method. Oh, like how can you put up with this? Like I mean, unless I specifically don't use this method of yanking. I don't know if this bug that they're reporting is visual mode. When using maybe I'm using the wrong. I want the whole line though. Gosh darn it. We convert this to C++, and then that's something I've been meaning to do. All right, take care. So let's see. Let's just this is I don't really want to be dealing with eno files anymore. Let's cut the cord. So I think we need function I thought there was a used to Platformio used to say, oh, are you sure you want to do this? Do you want a tutorial on how to do it? Sure. They had a document that I want to read through some. Here we go. Convert Arduino to C++. Is there an automatic way of doing it? Yeah, missing includes such as and function declarations are omitted. In this case, so we have to include a Arduino header at the top. Let's do that. Why my music stop? I don't know, Spotify. Okay. Declare each custom function. Before calling it. I suppose we could just move setup and loop to the end. Let's just try that. Setup, loop. Finish. Okay, that's it. So let's see if that works. So how do I exclude this? I guess I could just delete it. Do we have to have a main function, or is it just get that I've set up in loop? So I'm just gonna move this file out of this folder. Cut, and I'll just paste it in my Platformio folder. So this file is deleted. Yep. Okay, let's try to build that and see if. Oh, yeah. So we'll eventually make some proper declarations here, but for now, let's just get it working. Move that guy above. Let's try again. We'll flash our debug wire guy. So this ESP has a bunch of wires connected to it, so we can connect it up to our logic analyzer, and then we'll see this code in action on the logic analyzer. Upload port. Okay, let's try it. I didn't have it plugged in. I think that's what it's upset about. Hey, what do you know? Platformio doesn't have to recompile my code just because I forgot to plug in the ESP. My biggest complaint of Arduino. You see like people complaining about it online. And they're like, why would you ever do that? I'm like, you don't. You should just always recompile. Never mind that it takes 5 minutes to compile. It's not actually 5 minutes, but I probably could be. Depending upon your project. I think my noise canceling headphones just died to switch them over. Okay. So I think we just flashed it with our new code. Looks like it's going. Let's shoot some data over. Looks like we got it. We didn't get that last byte like we didn't before. I don't know if we're just stomping over the top of ourselves. We'll figure that out. But let's go ahead and, since we got our logic analyzer going, I guess I never saved my my new setup here. Do this again. Should have triggered our analyzer. Waiting on trigger. No, didn't get a trigger. Well, what is my trigger set to right now? Edit trigger. Logic change on signal 2. Maybe let's do all channels. Okay. Start. Go. No trigger. My wire's broken or something here. Let's just say no trigger. Start. Okay. No data, of course. Edit trigger. Logic change. All channels. Okay. Did I forget to click start? I mean, how could it not be? Oh. No, we don't actually have any data. Let's start over here. Maybe we weren't actually getting a logic change. Maybe that last byte has to do with we're not getting our interrupt like we think we are. Should be though. All right. Let's start our logic analyzer. And let's send the data. Okay. We got an interrupt, but no data. Oh, we didn't send the UDP packet. Now, what's going on here? Did we forget? So this is miso. Oh, you know what? I think we're this must be spy control, and I think this is Mossy. So I think maybe we forgot to take this high again. Fetch byte. Yeah. Oh, it's because we had it down here. Okay. Let's just look at this again though. So we take the, here's where the write, right now it's just INLretro, but the 6502 would write to the 5000 register. That W bit is getting cleared whenever that happens. Right, and this WSR bit is what we are connecting to the miso, so that's the least significant bit. Yeah, so we're just fetching the spy byte, just this one routine. Yeah, so we clock our data out, we take it back to parallel mode. let's just assume we fix things here and do the multi-line yank that I wanted to do last time. Okay. So we fetch the spy byte. Gotta store it in something. Send UDP. Oh, we have to. Do we do a UDP begin? I forget. No. Oh yeah, UDP begin packet. Then you write. Then you end packet. Oh, I made a function, send UDP, that does all of that. But if you want to construct your message as a write, then you can separate it out. So spy read, we have a character array 0x, write that. That was kind of my my debugging of using this. It'd probably be faster if we, but or debugging, whatever. I guess we could do like a debug print function that just does this stuff. Let's just put it here. Send UDP debug. And I think I just want to send a so print UDP byte, and we'll just send a what we should effectively be able to do then. Well, I want to fetch that first. Okay. So then we'll just call print UDP byte data. And let's put this up here. So begin packet. So we'll send 0x just to prove that string, so the data, we're converting it to hex, and then we write that. So I think we can leave this out. We can leave this uninitialized and send. So we UDP write the beginning of what we want to say. Then we convert data, the byte, into a string, and we write that, and then we're done. Now we're going to want to process, because the way this is really going to work is we're going to fetch that byte. We're going to have data, and that's going to be a command. We're going to go do something with it and respond. But for now, we'll just do a debug print to UDP so that we can see it. Now, this is probably more than we want to do inside an interrupt service function. We set some flag and have the main loop process the fact that we got more data. I don't know, but whatever. We'll just go with it. So let's put our... do this powered down. Now I think this code will just automatically use whichever, yeah, there's my updates are there. I think I might be close to ready to go to Platformio command line. I really, very little benefit I'm feeling here from VScode, especially because its Vim is wretched. All right, there's probably better ways. My interest in spending time figuring it out is low because it's not my preferred environment. All right, so I think it's flashed, and we can just plug her in. There we go. Send data. There we go. Let's check our logic analyzer. Start this guy. We'll send the data again. There's our data all over again. And our logic analyzer. See, there we go. So the interrupt is occurring at this point when the 6502 makes the write the INLretro right now. Then our interrupt service routine starts executing, and it calls our fetch byte. And the first thing it does is takes SPI control hot, low to serial mode. takes clock high, and then it starts fetching our data. So the first pull is like here. And then this is, so this is the W bit first, right? The W bit is coming out as soon as the parallel write happens. We pull, here we pulled the W bit, we end up throwing it away. Here we shift out the R bit. The R bit was set, which we expected, right? Because what did we do in the verilog? We set the R bit anytime a write occurs. So here we pulled the R bit, which we don't really care about. We could speed up our code a little bit by just clocking quickly. We don't have to sample and add and shift, but whatever. We can make a note to speed up the code, I guess. But anyway, well, and anyway, so here's the R bit coming out. Here we sample it. Here's the most significant, or the lowest bit, bit 1 coming out, and here was where we're sampling it. So the first byte was 1, right? The rest of it's zeros. Right, 1 was the first bit or byte that came out, and then here is actually we shifted. This is the data that's getting shifted in, all ones. So here on this very last clock, you see the first bit that we latched, the W bit, getting progressed all the way to the output again. So here it's going high, and then the function's done. We set it back to serial mode to let the 6502 write to the register. Okay, not too shabby. So let's do something intelligent with the information, I suppose, huh? I don't like 3 spaces. No, sir. I don't like it. The only other thing that I don't know is, it seems, so normally this interrupts get triggered right from falling edge. If you don't disable interrupts during your interrupt service routine, you would be able to cause another interrupt, which causes the processor to call your function again. Conceivably, so this falling edge causes a trigger. This falling edge would too. It would seem that this is already happening. only like verification we have that is just like visually, I mean, things are working. It's desired behavior. I'm guessing that Arduino just tries to be your friend and disable those interrupts for you. Which I guess is that's the functionality that we want. I'm just a little bit nervous. But whatever. I think I'm going to take a quick break. And we'll process that data and try to... We need to actually write something other than all ones to the shift register. But we'll do that when I come back. Got about another... I gotta leave about 1:40. I got something going on at 2 o'clock, so we got about another hour. So after I get back, we'll see how far we can get with that. Alrighty. So what do we want to do? I guess let's if 6502 requesting expecting a reply, send it. So we'll wrap this in logic eventually, but so let's for now, let's just invert the data. Is there a bit what we can XOR with? I think that'll just do it, right? Let's just do this. Data equals data. That'll be our processing. Or we'll do int reply equals that, and then we'll send. So then our data is preserved. It's going to be similar to this fetch by byte. So we're going to go to serial mode. Now we need to clear W and R bits. Int data. We're not going to send a reply yet. Till 652, it can write to R equals 0 tells 6502 our reply is in 5000. So part of me says that we could just pad that information into the data. This is an int. I'm guessing that an int is more than 8 bits. I'm gonna assume that until proven otherwise. Now, so to do that, we'll just say data equals data shift by 2. Maybe generally it's processor dependent. I think this is a 32-bit processor, but I don't know if Arduino default defines it to something. Whatever it is, it's not to be trusted or assumed, but we'll just assume that it's more than. We'll soon find out if it's only 8 bits. I can't imagine. I have a hard time imagining that it is. This isn't necessarily the fastest way that we could do this, but I don't much care at this point. Online chart tells me it's actually 30. Yeah, that would have been my guess, but just because it's I'm pretty sure it's a 32-bit processor. But the only thing is everything on Arduino 32 bits, or is like if you're on an 8-bit processor, is it 16? I imagine that Arduino wants everything to be the same, because otherwise code wouldn't be very portable from one board to another. So we don't want to clear data. Don't do that. So now we need to set or clear the MOSI pin depending upon the least significant bit of data. So if data ended with 1, else bit set bit clear. So we actually want to let's just go ahead and set SPI clock high. Because it's going to be the negative edge when we actually clock it. But we can also indicate that our data is about to come out, but we'll see our data go high or low anyway, whatever. Okay, so if the bit's clear, we're going to go digital write SPI master out serial in SPI MISO high. If it's clear, we'll set SPI MISO low. One thing that I really would like to, like, some of these like bit banging functions like can generally be sped up quite a bit with writing them in assembly. I'm curious if the viability of ESP I just don't know about inline assembly. Or making functions, and I'm not gonna jump down that rabbit hole yet, but but I'm interested in doing it to make this as fast as possible. The thing that I don't like, these digital write functions, like, are these macros? I want them to be, but I'm guessing they're not. I don't know. They could be inline. It could be functions that end up getting inlined with the compiler, but generally I don't like calling functions just to change the pin. I like to use macros anyway. So we'll set the bit. We'll go ahead and shift for the next. We are not going to do anything with sampling. So I think that'll just work, huh? Just set it back to control, to parallel. We aren't going to return anything. So just try that. I go to serial mode. The lower 2 bits should be, well, hold on a second. We actually want the W bit to be set. This being set to 1 tells the 6502 it can write again. This being set to 0 tells it that our answer is in this SPI register. I don't know if I like that convention or not. Well, I kind of do, because it makes fetching that byte quick. We always set the W, we always set the R, so we don't have to worry about twiddling the MISO or MOSI pin, the input to the shift register. It can just be set. And here we're intentionally so that should be what we want. So the W is set, the R is clear, and then we shift in that 10 bits. If data, and just looking at the lower bit, we're going to set MOSI high, else we'll set it low. We'll shift our data and we'll latch next bit, and we'll perform our next write. Okay. Let's flash her up. ESP device not recognized. $232. Needs more Wi-Fi. How we doing, Deedle? Oh, I suppose I would need a semicolon. That's what I get, switching back and forth from Lua to C/C++. Forgetting semicolons. All right, we're flashing error. Only got a 1 byte response. What's going on here? Let's try it again. There it goes. Okay. Let's give her a try here. All right, it's powered up. So we're gonna just run the same script, but the ESP, we don't have any interlocks for timing here. We can establish those by pulling the 5001 bit. It's just that we have pretty long latencies between USB packets. We won't have that with a test ROM, but it's kind of hard for me to test the status bits when my latency is so long. But we'll see. So we're going to write the data, but when we read back the 5000 register, I'm expecting, if we're slow enough on this read, and we can establish it just to verify, but we're expecting to read back the inverted value. It's processing of that value. So when do we get Bluetooth? When we upgrade to the ESP32. Bose sound dock, deep bass notes. There you go. Yeah, if we upgrade from the ESP8266 to the ESP32, these aren't that much more expensive either. But this, so the ESP8266, 32-bit micro, 80 megahertz. We overclocked it to 160 because why not? It seems to work. But 80 megahertz, 32-bit micro, single core. And it's kind of slow because it doesn't have any instruction ROM internal, only instruction RAM. So the code has to get buffered from the SPI flash into RAM. So it's a little bit slow in that sense. The ESP32, the successor, has it's dual core. This isn't telling us that it's dual core, but I'm pretty sure it is. Yeah, so it has a extensa, dual core, or single core. Operating at 160 or 240. And an ultra low pros. So is there possibly 3 cores? I thought it was just one super powerful and then one lower powerful. Like this is, I don't. It does have embedded flash. Ultra low power ultra low power coprocessor. Yeah, this LX6 can either be dual or single, and then we have a low power coprocessor. We have read-only memory, SRAM. I'm curious about this, but I thought it was like I mean, it is asymmetric in that these 1 or 2, but I'm surprised there's an option. I wonder if it's just that they have one die, and if one of the cores fails test, they just disable that core. or they disable by default unless you pay them an extra 50 cents, and then they enable. I can't imagine they have different dies. Maybe they do though, but anyway, I didn't realize there was an option. But this other core could be, you know, dealing with the NES side, and then one core could be dealing with all of the Ethernet side. Anyway, but we got a Bluetooth link controller. Yeah, we have cryptographic hardware accelerators, so we can have legitimate encryption. Yeah. I think the hardware SPI that's on the 8266 is dedicated to the flash. I don't think there's another one available, which is why we're having to bit bang it. The pins that we're using definitely don't have available, but if we upgrade, I don't think we get them either. Anyway, encryption for the NES. Yeah, if you wanted encrypted data, or if you wanted to like go peruse encrypted sites, you could have the ESP doing the decryption for you. All right, let's send this data and see what happens. Ooh, that looks good. I was never really smart enough to get what it really does. Encryption or the NES? It looks like we just did it. Maybe I can give you a 10-second rundown. Okay. I'll give you a 10-second encryption rundown if that's what you're saying you don't get. Of my layman's understanding of encryption. Anyway, so we wrote one. This seems, oh no, that's right. Yeah, encryption. So all it really is, very dumbed down sense, is modifying the data. Yeah, so we just encrypted this data byte. We took a byte, and what did we do? We XORed it. We inverted all of the bits, and then we sent it back. This is like a very basic encryption. We're just flipping bits. Now, where things get more complicated in the encryption sense is like, which bits do you flip? Making the bits that you flip look very random, and how you make them look random is the encryption scheme, right? The algorithm of deciding which bits to flip. So you have some complicated algorithm that takes, you know, readable text, and this, you know, here we can think of it as just a single byte, or like a message, right? Hello world, red fox jumps over log, whatever, right? We randomly flip bits in there. We massage the data, flipping a bunch of bits, and then what we spit out just looks like noise. But because you have the key that you're able to run through that algorithm, you know exactly how to massage that data to which bits to flip over and over again, whatever, to get the. But why do this? Well, because when you go to your login at your bank, right, you don't actually want your password and login information to be transmitted over the network. You want some random noise to be going over the network that only you and the receiver are supposed to know what the the pseudo-random sequence of XORing to get the end data out. The thing that I don't 100% understand is like, how do two parties that aren't, you know, how do you, somehow you have to remotely, well, and they get cracked. encryption algorithms do. But the best ones that are out there right now, like, yeah. The thing that's I don't understand is if both parties have this key, right? I understand how they can encrypt and decrypt data, but how do you communicate that key? Like, that's the part that I don't get, is like, if I'm sending my key to the other thing and say, here's our key that we're using, then I sent the key across the network. Why can't, is it just hard to find that key? Like, that I don't understand. But anyway. I digress. I'm running out of time though. I got less than an hour here, so I got to wrap up at 2. But so we inverted all the bits. We wrote 1. What's 1 inverted, right? It's all bits set except for the last one, FE. We wrote 5. We read back FA. The other thing is okay. So first, both 5001 bits 6 and 7 were set, right? C0 1100, both of them are set. We wrote a 1 and we read it back, and only bit 7 was set. Bit 6 was clear, which tells us as the 6502, hey, your reply is processed and it's waiting for you in the shift register. There it is, FE, right? 5, FA, writing an 8, reading back F7, yep, A, read back F5, writing A5, read 5A. So it looks like it's working. We could implement the basics of my instruction command set like I was talking about. We need to actually do something more meaningful than invert the data. Actually process that command byte. But the underlying hardware is all there to do it. Here's the other thing that we're missing. Thanks, Daddy Funk. So, the exchange using public-private key pairs. Yeah, public key cryptography. I'll have to check it out later, but that's what I don't fully have my head wrapped around. So how a public key is useful or gets made use of to still keep secrets. But yeah. So here's the one major hardware thing that I feel like we're missing. So we have a means of indicating to the 6502, hey, the data that you requested is done. It's ready for you. It's sitting in the 5000 register, right? And we do that by clearing this R bit in our reply. So when the 6502 writes to the 5000 register, it gets set. When the ESP reads the SPI register, it will set it for the first reading of the command. When it goes and processes that command and sends the reply, writes the reply serially back into the register, it will clear this R bit. That tells 6502 that its answer is sitting in that register. But what if the 6502 is requesting a string of data, right? I want more than 1 byte, right? One way that we could get around that is, oh, well, it would write something like send next byte. I guess that would work. And when we fetch the byte, right, it would just be, oh, send us the next byte. The other thing is, I guess that's probably the best way to do it, honestly. Now, we could have the ESP be in some mode where it knows that the 6502 is requesting a sequence of data. And instead of fetching the byte, it'd be like, hey, we're in message mode. When you got this interrupt, just blindly send the next byte. If the 6502 did something else, we would end up stomping it. But really, I guess that's about as fast as we're gonna get. The only thing that I guess might be useful is if the ESP could tell when the 6502 reads the byte. If the ESP were able to know that, then it could just send the next one. But I don't know, because how is the 6502 going to know that how is it so the R bit gets clear when the ESP tells, writes the response? There has to be some sort of interlock to where the 6502 knows, okay, now the next byte is ready. If a reading triggered that, if a read of the register triggered the ESP to send the next byte, we would have a problem if, well, I guess the mapper would have to clear this bit on a read. The only problem with that is then our mapper is not DCPM safe. If the 6502 gets interrupted by the noise channel while it's reading it, it's for the same reason that if you have samples and you read the controller port, if you have audio samples running, you read from the controller port, you should read it twice to make sure you get the same thing twice. Because if the DPCM unit interrupted the 6502, you would lose bits because you do 2 reads when you only had an instruction for 1 because that instruction got interrupted. I think I'm just going to leave this as is for now. It's the most basic and it's the safest. We could implement a faster option to where a read from 5,000 would cause an interrupt by clearing the W bit, but things are just going to get more complicated. So let's just stick with that. This does allow us to do everything that we could want to do. I don't know. I've only got about 30 minutes or so left. And I don't know that we have time to really take anything to the next level. We do want I was hoping to get started on test ROM today, but I just don't think it's going to happen. So I suppose we should, well, we can at least define. We can kind of set up we can get our pseudocode effectively for how the assembly code is going to look. The other thing that we need is doing something intelligent. I guess maybe we could work on that, but you like the schematics to be able to pretend? Yeah, it does. I mean, it helps me too. I'm glad that C boxes and text. Yeah, I'm glad that they help you out as well. So let's kind of. Well, I don't have a block diagram. We can do one here quick. So we're really in day 6 here. Let's do it, new page. So we've got the internet, right? We've got your home network, right, which is of course always connected to the internet. At least we hope. So your home network, you're going to have a Wi-Fi router or access point to this home network. And then we've got the ESP. I'll make this block big because it's huge. No, not because it's huge, but because it's doing quite a bit. So this is the ESP. Happens to be an 8266. 01 is the type of module that we're using. So there's two primary things going on inside this, as far as like the code sense, right? We have the Arduino libraries. Those are all of the internet antenna related things we don't really have to worry about. We just have functions that we can call to send and receive data. And then we have SPI bitbanging code, and this is what we've been working on today. This code actually has access to twiddle these 4 pins. We also are going to have our some sort of protocol for communication. So some sort of command set. This is where we're going to have variables that the ESP is able. So this, I'm kind of falling out of a block diagram here, but we'll just keep going with it. So our mapper chip has a shift register. These signals are connected to the shift register inside the mapper. And this is connected to the data bus of the 6502 inside the NES. And then, all right, we're going to have our code. So this is basically everything that's going on, but all of the pieces, but the this bit right here is what we've still really yet to design or define. We have some ideas of how this is going to work, but these arrows that I have here, these are really low level things that we've been working on. We effectively want these bits and pieces to be abstracted away from the developer. They don't need to understand this underlying stuff. We can write helper functions for the 6502 to get us access to this protocol here. So there's my alarm reminder. I still got 20 minutes or so. So here's kind of what these helper functions are going to have to do. Yeah, the mapper is written in verilog, and that's this code that we have here. So this is the entirety of the SPI register. There's a control pin that the ESP drives to decide whether this register is written to in parallel by the 6502. Yep, end goal is to send data over the network to the 6502, well, and back and forth, right? So, really to do anything, right? Connect all the dots, but you know, this could be some other players has the same network setup, right? And the other thing, so how that looks exactly, whether there's a server or whether it's peer-to-peer, we have, you know, control over how we want to set that up. I want the ESP library that we create for this protocol to be able to basically support any method that somebody chooses if they want to set up a server, or there's a community server that's set up that's able to be used, or if you want to directly connect, you know, I say connect, but if you just want to broadcast UDP to the other player or players, the ESP will be able to handle all that. So that the lowest level stuff, and this is wouldn't actually be in the helper functions. This would be the mapper interface layer, I guess. If we change the register, the verilog code, then this layer would have to change. But I'm hoping to keep things layered so that like these helper functions don't have to change if we change the hardware. If we change the hardware, you only have to change the hardware. I don't know, this is really the phi, right, of the communication going on here. Did not want to erase. But okay, so let's say we want to write a byte, or we want to write a command. Yeah, all this stuff is I'm hoping to make as much of it open source as we can. whether or not I'll go so far as to open source my PCB layout, not 100% on that, but if somebody, part of the thing is the schematics, yes, and the verilog, I mean, I've been sharing it online, whether or not I want to help people debug their CPLD problems. More of like, come to me if you want to make your own version of this, but we'll see. The software, though, all open source. So we want to write a byte. What are we gonna have to do? We'll have to check wait for 5001 bit 7 set, because if that bit's not set, we cannot write to the 5000 register. Write the command to 5000. I guess the other thing that we've yet to implement that we probably will want is interrupts. So the 65 or the ESP can interrupt the 6502, but we'll wait for that. So we write the command to 5000. The ESP will get interrupted. It'll go fetch that byte, just like we've been working on today. It's going to go process that, and it's going to realize, oh, I don't need to do anything. I'm waiting for more. The ESP is waiting for more data. But in the process of fetching that first byte, it's going to set 5007. Wait for 5001 to be set. Write data to 5000. Now, for all intents and purposes, this is done. Right? We could write another byte. All we have to do is make sure that 5001 is set before we do it again. If we want to read a byte, we have to check wait 5001 set again, just as before. We can't communicate until that's set. We're going to write command to 5000, right? And that command's going to be, you know, I'm writing to this variable or whatever it is. Wait 5001.6 is clear. So the 6502 wrote its request to 5000, and the ESP will get an interrupt. It's going to see, oh, you sent me a command that you want to read a certain variable, whatever. It's going to go fetch that data. And it's, so the first, when the ESP first reads the command, it's going to set bit 6. But when it processes it and it goes and writes its reply, it's going to it's going to clear that bit, letting it know that, so now the 6502 knows that, hey, your data is in there, so wait for 6502 clear, and then read your data at 5000. Now, if you want to read another byte, you just repeat that again. You can't, you need to send the command for next one. So this will let us do everything. We can just add more complexity for speed improvements. My basic idea for these variables that are inside the ESP, there's going to be can I copy that? I don't know. Doesn't like it. Copy. iPad's slowing down here. This is the addressing mode that I want to use. Not my iPad's. There, it's copied. How do I paste? I don't know. Anyway. This is not. There it is. It's super slow. Oh, you can't see it though. I don't even. Well, that didn't work. But anyway, so we have bit 7 is read, write. 6 is immediate. I can't count. I said 64. Yeah, so this is going to be the variable number. Now, I think I want to set we can have 64 readable variables and 64 writable variables. Or we can have some of these variables just defined as read or write only. But So kind of just think of this as an array of registers or variables, a list. So this is read only, this is write only. If so, the read only, this is the remote variables. The write only, these are the local variables. So we got, 0, 1, 2, 3, 4. If you write to variable 0, right, your local, the ESP will say, oh, you wrote to variable 0, right? I need to broadcast that update so that other remote machines can update their remote version of it, right? So then if you want to read variable 0, you're reading from the remote version. So basically, if you have player 1, player 2, right, you can always think of the local version as player 1 and the remote as player 2. All right, we'll see you next time, Dizzy. I'm just wrapping up here anyway, so yeah, but this is what I want to do for the first set. Now maybe some of these variables, right, maybe some of these ladder, maybe we don't use all 64 for this register file. Maybe we use bit 7 as control variables. I don't know, but this is kind of what I'm thinking. We also, we're gonna try to lean on some of the definitions of the rainbow mapper that Broke Studio and those guys are working on. I'd like to try to make things compatible, but yeah, so these variables, right, updating and broadcasting these variables, that's going to have to happen here. We need to process the data. So I'll make this quick recap. I kind of been recapping for a while to some degree, but we implemented the main thing that we implemented here is there's now an R bit, status bit in the 6502. It's bit 5001-6 or bit 6, and we migrated over to C++ on the Arduino code so that we can edit in Vim and get our highlighting. We now have, so here's our interrupt service routine. We just call fetch by byte, which is similar as before, except there's no UDP printing. We need to work on processing that command, but we effectively have that command as a placeholder for right now. I just XOR all of the bits of data and then write it back to the SPI register. So our send SPI byte is what we worked on. The SPI register is 10 bits long now with the R bit, but it's going to clear the R bit to tell the 6502 that, hey, the response that you were looking for is now in the SPI register. So it's very similar to our fetch loop, except now we don't care about what's coming out of the register, only what's going in. So we just check the least significant bit, and we set MOSI, shift the data, latch the bit, and send the next one, and then go back to parallel mode. So serial. We cleaned up some of the code a little bit, and yeah, we have a logic analyzer trace here. Here's where our MOSI pin goes low to give our interrupt. Here's the oh, let's run it quick because we'll be able to see the reply as well. So this is just the, we haven't ran the logic analyzer with the new setup with the reply. So we'll go ahead and start that. And we're going to, so we write a 1 and then we read back the register, and it's the inverted value, FE. That's what we're expecting. And here's just when we get done with the interrupt, we just send a UDP packet or whatever the data was, just as like a debug. So here we can see this is the data that we got. Our logic analyzer should have caught that, and here you can see it. That was pretty quick. We got 49 microseconds total. Anyway, you can see here's the output of the SPI register. It went low when the 6502 or the INLretro wrote to the 5000 register. Here's the parallel, right? The control pin goes low for serial. The ESP clocks out the data, and it's pulling the MISO pin, right? And then here it's done. It goes back to parallel mode. Now, this time is actually when the ESP is processing that data. Right now it's just inverting all the bits, and then it writes the output, right? So it has to go back to serial mode, and it's clocking in the data. And now 6502 or the INLretro is able to read that value out here. Okay, we don't actually have an indication of that. Here's the next write. But yeah, so we officially have two-way communications, response being sent back. The next things we need to work on is actually doing something with this data. So we're transmitting a message or updating. We work on our protocol definition. I have this idea for basically a register file, variables that the local machine can update for player one's copy of the variables. And when the ESP sees that the 6502 is writing, right, that's gonna be one of the commands, update this variable. It's then gonna be like, okay, well, the other player needs this, and it's gonna update, the other machine's gonna update the remote copy. So there'll be read only for the remote machine's copy of the variables, and there'll be write only for the local machine. And the ESP is just going to, behind the scenes, make those updates so the 6502 doesn't have to, oh, send this data to the other machine. It's just automatically going to send it over. For turn-based stuff, this is all that's really going to need to happen. You could get by with just one variable, right? What's the controller state? So that's where I want to start next time. We need a test ROM. We also need a way for the 6502 to communicate, right, the IP address of the remote machine that you want to connect to. So maybe we'll just start off by having some of these bytes in this register file be the remote machine. I don't know, the IP address. Maybe not. More thinking on that. We have our basic read write byte commands. So when the 6502 wants to write, we check the 5001 is set, we'll wait for it, then we can write the command to 5000, wait for it to be set again, then you can write the data. If you want to read a byte, check that 5001 is set, write the command, then you wait for 5006 to be clear, then you can read the data in 5000. So these things are enough to, this command would include, it would look something like this, right? Bit 7 is set or clear for read or write. This bit is set for this addressing mode, and then bits 0 through 5 is the variable number, right? Which number in this register file are you reading or writing from? And then the data is the value that gets updated into there. So we have a nice little block diagram of what's going on too, which we got into a few minutes ago. So hope you guys have a good weekend, and I'll be back next week, most likely. Actually, probably not. I'm not 100% sure what's going on with the holidays. These next 2 weeks, we'll just see. I don't know what's going on, but yeah, thanks for stopping by, D-Rocks. Thanks for, yeah, that's all right. Polymath. We'll be back again. I need to get these posted on YouTube. I'll try to do that, at least at a minimum, get these posted on YouTube. They are on Twitch for yeah, thanks for the follow. And thanks Duddy Funk for stopping by. Twitch always has the streams for 2 weeks. If nothing else over the holiday break here, I'll get my backlog of the project loaded up to YouTube. I always try to do the recaps at the end, so, and put a description in the links to the recap. So if you find them on YouTube, I'll make a playlist or whatever. You can go straight to the recap at the end instead of watching me struggle through all my daily troubles here. But let's go ahead and